Thank you for the introduction. And I'm Oswanio, I'm our guy. So again, sorry. I've tried with this fancy title, Photonic Engine, the key to the future of deep learning is just to introduce the fact that there are a lot of potentials. And in this hour, more or less, I'm going to try to explain to you what is the potential of photonics and how it could enable accelerators for deep learning. So we'll see. So here I added the question mark because it's not really clear if photonics can actually be that helpful. There's a lot of questions that are still need to be answered. And I'm going to try to give you, let's say, some trends and how this could effectively be a solution. So in this investigation, I'm going to try to unveil you this emerging field because it's something that's been recently starting. And in particular, I'm going to focus on deep learning and AI. Since I'm not from machine learning or AI, I might say a few things that are not totally correct, so sorry for that. I just look at it from other perspective. So sometimes I might cite some things that are not correct, but because I'm not really an expert on AI. So after a few opening remarks, I'm going to give you some historical evolution of optical computing, because I guess you don't or you have never heard of optical computing. So is there anybody that's heard about optical computing in the past? So 1, 2. So really little has been, let's say, how can I say, it's not something that is really well known. But I will show you that actually it's something that has been around for a long time. So I'm going to try to go from the historical perspective. For you to understand a bit better what is photonics accelerators, I'm going to give you some basics of photonics. So unfortunately, I cannot do much, but I'm going to try to quickly explain to you how integrated photonics works. So I will show you what are some photonic engine examples. So how it could be the next frontier, and what could be the advantages of photonics. So I say the good because usually people, they tend to focus on the good things of photonics and say, yeah, it's fantastic. I will try to actually show some real world applications that have been developed in the last few years. And I'm going also to tell you about the technological challenges. And this is the bad, because most of people, they just overlook those aspects, but it's important to actually keep in mind that there are still a lot of challenges that need to be overcome. And finally, I will try to give you some future perspectives and trends, and we'll see that the trend is not so ugly, and that there is some hope for photonic accelerators. And if I have time, I will address some extra topics, but since we're running late, probably it's already too late. But anyway, so light-based computing is a story that actually starts quite some time ago. In fact, the CERN in 1978, so we are speaking almost 50 years ago, they were already using it to process data of particle accelerators, and we'll see how and why it's ultimately failed, because it's something that has been developed over the 80s, 90s, up to the beginning of the 2000s, and basically it's technology that kind of died, and now is basically getting a new rebirth thanks to integrated optics. So, so it is actually older than you think. So because you might have seen some fancy papers recently, but it's something that is almost 60 years old and even more than that. It has been used by, for example, US Air Force and DARPA in the 70s for rockets and missile guiding. So it's something that has been used. Even a general purpose computer has been designed and built in the 62s. Obviously, we'll see that it was what they call computer, because at the time computer was not exactly the same meaning as today. Optical processors have been developed in the 90s, and we'll see some examples and how it works. And at the heart of photonics is the use of light. So it's something that I'm going to stress is that how we can use light to actually do computing. So if we look at an historical evolution of optical computing, obviously you don't see much here, but it is something that actually goes back quite a long time ago. And here I actually put two colors. So one on the left-hand side is before the laser is actually has been discovered, and after the laser has been discovered. And you see that before the laser has been actually developed, there was already a few implementations of optical computing, if you want. And actually, one of the first, let's say, ways of using optics to do computation, what we call Foucault's knife test. So it was a way to actually compute the defects in mirrors. And that, I mean, I'm not going too much in detail, but it was a way of using light in a certain way to actually compute the defects on a spherical mirror. And from that, there are other setups that have been developed, in particular, one that was, let's say, before the discovery of laser was Gabor's hologram. So holograms that actually came before the laser. They were invented a few years before, and it was a proposal of how we could use current light to actually build 3D images. So as you may know, laser is a very current light, and it was actually used later on to actually do processing. But before its invention, people were already actually using light in different ways. So actually, it's quite an old idea, and it's been starting more than 60 years ago. Let's say the idea of optical information processing is based on the idea that basically you can use the speed and parallelism of light because of the to process information at a very high data rate. Yes. Okay, so we lost. Yeah, the connections between C. Sorry about that. Okay, so we're back. Okay, so and it is thanks to a very particular property of the light is that if you take so an instant light that is coming into an object plane, what we can see is that this object plane, and you put it at focal length of a lens, basically what you are going to get, end up with is at the focal plane of this lens, something that is a good approximation of a Fourier transform of what you had on the left-hand side. So here the idea is that, okay, we have something that can actually do the Fourier transform of whatever is on the left and bring it to the right. And it's immediate, basically. It's just a time of light that goes from one side to the other. So here the idea was, okay, so what if we actually use that for doing actual computing? So here the idea is that you have something that is going to encode data on the left-hand side. You have your lens, and on the right-hand side, you are going to get the results almost immediately. So that was one of the ideas, was to actually implement what's called a correlation engine. So basically, you have a picture that is coded by something that we'll see is called a spatial light modulator that goes through this configuration. And basically what you get is the correlation between your image, and here we have a reference plane. That's something that has been already encoded here that is going to do the correlation instantly with your incoming image. And according to the result that you're going to get on the correlation plane, basically you can decide if the image that was at the beginning corresponds to what is your reference plane. So here in this example, basically you have a picture of a plane, and you want, and let's say it's a system to detect the plane. Basically, you put a reference image on the plane in the middle, and basically, if there is correlation, you will see some amount of signal that is going to correspond to this information. And you can actually decide if it was effectively a plane or something else. Okay, so was, let's say, a kind of identification network that you could do, and it is something that basically was developed in the 60s. So how do we do that? So we use what's called a spatial light modulator. So how do we control the lights entering the processor? So basically, we are going to put, so from a practical point of view, you are going to put a plane, and in this plane, you are going to modulate the intensity at according to different pixels. So here we have, for example, an example of what you can buy now. So it's what's called a SLM, and when the light goes through this spatial light modulator, basically what's going to happen is that you are going to be able to actually encode the intensity of the light and the phase. The first, obviously, they were very cumbersome. They were based on Pocket cells. They needed a very low temperature, so it was something that was not very, useful. After there was the invention of liquid crystals, so in '75 more or less, and there was development of let's say high-speed SLMs that could work in the megahertz region. Nowadays, we can find, this is something that is commercially available, so we can find something that have, for example, more or less, so it's a typical configuration, so it's 1900 by 1200 of, so more than 1 megapixel, so you have 1 million pixels at the same time, and what you're going to be able is to actually use that to encode your data, so from the point of view of the input, and you can also use it to do processing. So here you can also, for example, so here is what we call the golden age of optical computing. So it will be in between the 80s and 2004. So it was more or less corresponding with the developments of those SLMs. So was development of the first optical information processing units. So here, basically, what you had is you had optical pattern recognition based on optical correctors, like the one I showed before. Developments of systolic arrays for processing, so more or less 86. Matrix inversion processors, and even machine learning optical neuromorphic processors in 88. So we are speaking of more than 30 years ago. So there was already implementation of machine learning optical neuromorphic systems. So here you have an example. So cannot see very nicely, but anyway. So here the idea is that you are going to encode vectors and matrix, and you can actually use this kind of configuration to actually perform matrix multiplication. Okay, so you end up with one pass, basically from left to right. You get the result here at the output plane here, which is a multiplied by x. Okay, so here everything is done in one go. So here you don't have to wait anything. You just get instantly the results. Okay, and here it only depends on how much pixel you can actually put and the size of your matrix. So in the end, here you could obtain, let's say, 1 million results in one go without any problem. So here's another example. So here is an example that was developed by NASA, and so it was actually what they called an optical computer. So it is some kind of processing engine. Here you have exactly the same idea. So basically you had a processing unit where you have an input plane, goes through a series of lanes, and at each intermediate here you have other SLMs that are going to encode, let's say, matrix or whatever you need for doing the processing. So the system clock was around 100 megahertz. So if you compare to what was available at the time, so we're speaking of 68 or 40, was 25 megahertz. So basically, in terms of raw power, is more or less the same. But you could here use an array of 8 by 8 diode lasers at the same time. So 64 channels in parallel with around 400 megahertz bandwidth SLM. You could, so if you aggregate all the data you could put at the moment, it was around 12.8 gigabit per second. So if you compare what you could do at that time, so here it's we are speaking of 91. The top computer was around 20 to 20 MIPS. And the best supercalculator was around 1 gigaflop. It was Cray 2. So you have something that was filling a room that could give you 1 gigaflop. And this thing here, which, I mean, according to the papers, was something like a table, basically was able to actually perform operation at more than 1 terabyte binary operations. So more than 1,000 times what you could do with a computer. So here is what let's say the caveat is that the only thing that could be performed this type of computer was minterms and an OR. So you could do like logical processing. So it was not really a computer with an OS and with all the things that you could think of. But remember, it's 91, so we are still speaking of DOS. We are still speaking of was not even Windows 95, so it was still Windows 3.11. So we are thinking of at the time where basically computer was something that just was for crunching numbers. Okay, so for people at that time, that was the best you could do. So, but ultimately it failed, and it was, I mean, a lot of different reasons, and one of them was the telecom bubble. So in 2001, I don't know if you remember, there was the telecom bubble. Basically, everything crashed, and basically there was too much, let's say, hype on optical technologies, and it kind of killed everything about optics. So basically, in 2001, nobody wanted to hear about optics anymore. Then the semiconductor was in crisis, obviously, and nobody wanted to invest in new promising technology. So they were just, okay, we want to cut everything, we don't care anymore. And there was another new technology that was arrived and was very promising, the GPU. So here was the beginning of for 3D application, gaming, etc. But started around 2000. So basically, you had this new technology that was very promising, and on the other hand, we had this let's say old technology that was okay, nice, but there was a problem that no mass production was easily foreseeable, because here you have lenses, you have arrays, or everything is very tricky to actually be made. So to think that you are going to do that in mass is tricky, and technology was still cumbersome and memory limited, and I'm going to speak about that in a second. So yeah, I would like to give you kind of my a personal feeling, because I've seen development of all those things. So basically, in the 90s, you had development of semiconductors, and basically we're saying, okay, we are going to hit the end of Moore's law in a few years, so we need to change. And people, they were, let's say, thinking that in 10 years, maximum 20 years, basically we are going to have photonic computers. Obviously, never happened. So then we have the same thing in 2000, and at some point, so it's continued to evolve like that up to the beginning of 2000, and basically people were still saying, okay, we are going to get photonic computers, but in the end, never arrived. And now what I'm going to show you is that maybe because it was the wrong idea. So not to do a photonic computer, but to do something that's going to help electronics. So another thing that is important is that the optical computer, it was failed because it actually needs the electronics anyway. So if you want to have the capacity to tackle real-time large amount of data, you still need to feed it. So you need to have something that is going to bring the data into this optical processor. And I call it, how do you feed the beast? Because, okay, you have this thing that is capable of doing the processing at 1 tera flops, but in the end, especially 2 decades ago, there was no technology that was capable of actually feeding that amount of data easily, or it was very cumbersome and very expensive. So how do you mass produce these optical engines? So it's a considerable effort were made to actually miniaturize those optical engines. But anyway, when you need to align all these optics, it's very tricky. And in the end, nobody actually found a way to actually make millions of them in a very efficient way. And there was the question of why invest in billions for another technology when we already invested billions for semiconductors. So why we keep doing the same thing? So CMOS, GPUs, and so on. So we already we continue to develop on electronics. So there was really need to show. So there's really a need to show a competitive edge. At some point, probably the market is going to uptake this technology if we can actually show that there is this advantage. So here comes the new age. So we are speaking of 2010, and basically here we have the need for advanced computing. So if we look, so probably you already know this better than me, is that before 2010, you had a growth that was basically following Moore's law. And since 2010, we have this kind of increase in the requirements for processing that was more or less doubling every 3 or 4 months. And here, basically, we need to, and you cannot see, but here, in terms of the amount of data that you need to process, there is a huge needs. So here we need to increase more rapidly the computing power. Okay, so and this is due to the fact that we have need of machine learning, AI applications. So there is this need here. Then we have another thing is that the big problem with the current trends of AI and machine learning, at some point, so here you can see it's the power consumption compared to the world's energy production. At some point, we are going to need, we are going to have that the AI and machine learning needs in power, in terms of power, if we continue this trend, is going to reach what the actual world can produce in terms of energy. And they estimate around 2030, 2040. So it means that at some point, we are going to be limited by the amount of energy that we can actually use. So either we find a new source of energy, so maybe fusion, I don't know, or we try to find something that is better, so more efficient. As you may know, there are already a series of new solutions that have been proposed. So we have proposals in in-memory processing using memory store, analog computing, developments of specific units for processing, NPUs, TPUs. I call them whatever PUs because now every now and then you have a new type of computing units that is appearing. So whatever PU. So maybe in a few years there will be something else. So here the idea is that why not? Why not photonic accelerators? So here we have another shot for developing this new technology. So there is also some interesting developments at the same time. So in parallel, we had since 2010 the integrated photonic has been rising. So I mean, in the 90s, basically you had maybe 1 or 2 functions inside a single chip. Since 2010, there was a growth in the integration of optics, and now you can find thousands, if not tens of thousands of integrated components on a single photonic chip. So we had this raise in the number of functionalities and basically in integration. Mass production of integrated optics now is being developed since 2010, and now I will say more on that later on. But here the idea is that since 2010, there was the development of what's called integrated photonics. So how we can integrate all the functions inside chip size elements. Then, since we have this development of integrated photonics, there was also development of co-design of electronics and photonic systems together. So, and it's something that is rising up years after years. So, probably there will be more evolutions on that. And as the complexity of systems has grown, the integration of heterogeneous system is no more, let's say, a taboo. Because before, in 90 or 2000, if you were saying, okay, I want to put different dyes together, well, people will say, no problem, don't think about it. Now it's almost something classical. I mean, you put different chiplets, you connect together, and you can use them with no problem. I mean, on a SoC, you can have many different systems together, and basically the barrier has been overcome. So also at the same time, the let's say the evolution of memory speed was quite tremendous. So now, if you think of what were the memories in 90s and 2000, they were very slow. Now we are speaking of HBM with gigabytes per second of bandwidth. So basically now we are shrinking the gap between what is the bandwidth of photonic computing and what the memory is capable of doing. So basically, we are reaching the point where basically we can have memories that can keep up with those photonic engines. And willingly or not, I know it is something that you've probably heard a few times, is Moore's law is getting to a stop, or at least as we know it, is going to be difficult to get more and more out of a silicon chip. I mean, I know that TSMC has already said that they were going to, they started to work on a node which was below 1 nanometer, but I mean, it cost billions and billions of dollars, and it is going to be very difficult to go beyond that. So at some point, we are going to reach our limit. So before I go on, I would like to give you some basic of photonics. So I will try to bring you from fundamentals to full system development in less than 10 minutes. Okay, I know it's not quite as possible, but I'll try my best. So we'll start from the beginning. Wave Maxwell equations. Okay, don't get scared. That's just to show you something. So Maxwell equations is what basically governs the electromagnetic field. And if you develop it, you can it leads to what's called wave equation. One of the simplest solution is what you find here, which is the plane wave. So you have a field. So maybe I can rewrite it here because on the screen really don't see it much. And so we have Maxwell equations. I know it's a bit scary, but in the end, you have that the field is E0 cosinus omega t minus phi. Okay, so very simple. Minus k is yeah, was the most important bit. Plus phi. So here we have different elements. So we have basically a wave with a certain amplitude E0 that is propagating along a direction z. So kz is for the propagation at a certain frequency omega. And here we have a random phase. And one of the things that we can actually play with, and that's one of the things that I'm going to try to explain to you, is we can actually play with different things. We can play with E0, so with the amplitude, so we can encode data using the amplitude. We can use an encoding on the propagation. So here we change the phase, and we can ultimately also change the phase here and the propagation together. So I'll try to tell you a bit about that. So what is a plane wave? So just to be sure that you get it, it's called the plane wave because basically you consider an infinite plane that is propagating, and the amplitude is oscillating at a certain frequency omega, and it's propagating along propagation vector that we call z, and the field is propagating this direction. So here we have that our field x is basically cos or sine omega t minus kz. So it's oscillating at omega t, and it propagates in one direction. And one of the things that is important is that on this plane, so in this infinite plane, the electric field has the same phase. So why is this important? I will tell you in a second, but that you need to keep in mind that on this plane, you have the same phase of the light. And one of the interesting things, so I'm not going to do the demonstration, is that you can actually prove that any other kind of optical wave can be decomposed as a sum of plane waves. So you can have any type of waves, spherical, whatever, you can actually decompose it into a series of plane waves. So plane waves is the base of, let's say, optical wave propagation. So once you found a solution for plane wave, basically you can put it with any type of wave. So this is why we always start with plane waves and see how it works. And why is this phase important? Because when you have two plane waves that are going to meet at a certain point P, so here the idea is that they have the same frequency, they have different, they are propagated from different sources, and they are going to meet at some point E. And the point is that when you look at what is the electric field at point P, basically it's simply, so the E1 plus E2. But pay attention that here we have arrows. So we are speaking of vectors. So it means that here it's not a simple arithmetic addition. It's a vectorial addition. And that means that when we are going to detect the light, what we actually are interested in is the intensity of light. And intensity basically is the square of our electric field, our vector field. Okay. So if we expand that, basically we get that E1 plus E2, we have E1 square plus E2 square plus 2 times the cross product. And this cross product means basically that we can have interferences that can be constructive or destructive, meaning that at point P you could get that the actual electric field could be 0 or could be twice, according to how they are going to arrive or not in phase. So this is what we call interferences, and that is due to the wave nature of light. So it means that basically when you sum light, you don't have this kind of, I mean, it's not 1 plus 1 equal 2. You have 1 plus 1, but it depends on the phase that you put. It could be 0 or it could be 2. So you have this extra feature. So why I'm telling you that is because when we look at the interaction of light, so here we consider something very simple. So I'm going gradually. When you have a plane wave that goes into against another medium, so here we have a clear interface. Basically, we have one plane wave that is reflected and one which is refracted. And here, I'm not going to do again the demonstration, but the only way for those waves to actually exist is that if they are in phase together. If they are not in phase, basically they cannot coexist. And if you look at the conditions, that means that the angle of incidence is equal to the angle of reflection. So I mean this kind of normal, but it also gives you a condition for what is going to happen for the refracted wave. And this is what we call Snell's law. So I mean, it's that sine theta 1 over n1 equals sine theta 2 over n2. So I mean, probably something that you've seen in high school, but anyway, just to remind you that it comes from that, from the fact that to exist, those plane waves, they need to be in phase. And if we look at that, what happens is that at some point, at a certain angle, basically we have what's called total internal reflection, meaning that all the light is going to be totally reflected because there are no possible waves that can propagate into the other medium. And this is something important. So here is an example of total internal reflection. So this is the swimming pool experiment. So it's something you can actually try. You go underneath the water and you can see actually your reflection at a certain angle. And you will see, and this is due to total reflection, internal reflection. So we can do the same thing for planar waveguide. So basically now we use a medium and one which has a refractive index and that is larger than the cladding. So the refractive index is, let's say, a property of the material. And if you do it properly, basically there are some rays that are going to bounce inside this plane wave, this planar waveguide. And if we look at the conditions between the different waves that can propagate, what we are going to find is that only certain angles can actually propagate inside this planar waveguide. Meaning that here, for example, from the point of view of the vertical propagation, since you need to have that the phase of so it needs to stay inside this medium, basically what you are going to create is what's called a standing wave. So you are going to have something like a string when you pluck it, basically you will see different configurations. And this is basically what we call modes. So inside this waveguide, you have configuration of lights that we call modes, and they correspond to those configurations. So we have for m equal to 0, so you have one lobe. We have two lobes for m equal 1, 3 for m equal 2, and so on and so on. And basically, that's the principle of guiding light inside a planar waveguide. There is a limited number or limited discrete number of solutions that depend on dimensions. And if you do it right, you can actually have only a single solution, which is called single mode propagation. This is something that is applied for optical fibers. So exactly this principle. So basically you have one core, one cladding, and what happens is that light is going to bounce inside, and you are going to have a certain amount of modes that can propagate inside the optical fiber. And according to the properties and the wavelengths you are going to enter the optical waveguide, basically you are going to have only one waveguide. So now you can actually do it in 3D, and you can actually do it in silicon waveguides. Okay, so here the idea is that you are going to define waveguides that are going to contain lights. Okay, so going to go a bit. So and we can build basically some building blocks that are more or less equivalent, not exactly equivalent to electronics, but we are going to be able to build waveguides. We can build splitters. We can do gratings for IOs. We can integrate lasers, photodiodes, etc. So I'm going to go quickly here because so one of the ideas is that if you want to do a coupling, you are going to exploit the fact that light inside those waveguides, they have what's called an evanescent wave field. So meaning that it's going to go around the initial waveguide, and if you put two waveguides together, basically they are going to bleed one into the other. And you can actually use that to actually couple lights from one waveguide to the other. So you can actually design couplers with different ratios. We can actually design, so here I'm going to go quickly, is what's called multimode interference coupler. So basically here we use one of the properties of light is that when you enter like a medium like that, you have diffraction, and the diffraction is going to create what's called a Talbot carpet, meaning that you are going to have a property of a nice property of light is that what's called self-imaging. So if you enter from one side of a confine, at some point you are going to find again the same image. So, and it's going to repeat again and again and again. And you can actually use that to create splitters. So this is a typical 2x2 MMI, where you are going to be able to actually split or recombine lights. For example, here is a 2x2, but you can also design for 3x3 or any arbitrary number. And that's something that you can do. So here comes the more interesting part, is we can actually put things together now to actually create what's called a Mach-Zehnder interferometer or a modulator. So here, basically, the idea is that you are going to split lights in two different branches. And these two branches, they are going to have integrated on it what's called a phase shifter. So we are going to act on the light that is provided in one of the branches. And if you do that, due to the fact that when they recombine, they are going to have different phases, basically, you are going to have the outputs, something that is like that. So you are going to have a modulation of the intensity of light. So you can actually use that to modulate light inside these elements. So we can use different technologies. So one of the simplest one is basically you are going to create what's called a thermal phase shifter. So locally you are going to put some heating elements, and you are going to heat the waveguides locally, and it's going to change the refractive index due to what's called the thermal refractive coefficient. So you heat up locally, and basically you are going to tune the phase that you have in one of the waveguides, and you can actually use that. There are other effects. I'm not going to go into much detail, but you can use carrier injection. So you can inject carriers, meaning that you are going to send electrons and holes that are going to recombine and change locally the refractive index. Those are very fast, so in the order of nanoseconds. You can use MEMS to actually approach something that is going to interact with your photonic waveguide, so it's something more mechanical. And it has around 100 megahertz of bandwidth, or you can use what's called carrier depletion. So now we put the carriers before and we remove them, and this is even faster, and we can get up to 50 gigahertz or even more than that. Another element that is interesting is what's called the microring. So the microring is, here we have basically a coupling here, and we close the waveguide on itself. So what happens when you do something like that is you have that the light is going to circle into itself. And when it does that, you have that the condition for the light to exist in this loop is that you have the exact phase here at the beginning and at the final phase. So it needs to have exactly the same phase when you enter this microring and when you get back after the loop. And this gives rise to what's called the resonance. So basically you can match this condition only at certain wavelengths. So it means that from the point of view of what you can observe, you have that the transmission is going to be a series of notches. So basically you are one of the, those correspond to resonances, and light is going to be in resonance and stay inside the microring until basically it escapes due to the losses. Or if you put another waveguide, basically they are going to be dropped and sent into the other direction. And this is going to be something that we can actually use to select single wavelengths that are going inside the waveguide. Then we need to enter inside our devices. So here again, I'm not going to go too much into details, but you can design what's called grating couplers, where basically here you are going to use the fact that when you have a grating, you are going to couple outside due to this geometry of the grating. And if you do it right, basically you can output the field in such a way that it is going to have the same shape of an optical fiber mode. So that means that basically you can go out of a chip and you can enter through an optical fiber. And this is something very useful because obviously you want to actually inject some data inside. Okay, so I know it was very quick, but one of the things that you can do actually is you can start to implement some optical subsystems. So here the idea is that you have one laser that is going to send one wavelength. You have a first Mach sender that is going to let's say, so here it's a broadcast approach. So we are going to implement some kind of modulation on the intensity. And then you split in different branches, so n branches. And each of those branches is going to have a corresponding Mach sender. And here we have on the receiving side something that is going to be capable to actually interpret that as an output. And here we have this configuration where you have two photodiodes. When we are on the top one, basically we consider this is a positive sign. Where we are on the bottom one, we consider this minus sign. So basically you can have something that gives you a signal that goes from -1 to +1. And that you can actually use that as a very simple neuron. You can use that as a very simple neuron. So this a first construction of how we can implement photonics neurons. So now I'm going to show you some example of photonic engines. So this is an example. So this is a graph neural network accelerator using silicon photonics. So here the idea is that when you want to use this kind of GNN inference, you probably know this better than me, is that you need to input the graph to be processed, you need to have an aggregation phase, and you need to combine it. So that is something that actually, these three main stages, you can actually implement it using photonics. So here, basically, the idea is that you have your waveguide, we enter with different wavelengths, and each of those rings that you can see here is going to modulate one of those wavelengths, and each is going to encode some parameter data. And at the end, basically, you have photo detection that is going to see what is the result of this specific wavelength. So if you do that, basically, here I'm going quickly, you can actually build an architecture that is going to do this GNN accelerator. And you can, here you have the three main units for this ghost architecture, where we have the aggregate, combine, and update. And it was here in this workshop, I put the paper on the, if you want to look at, they do in parallel different number of execution lanes, and during inference, each of the lanes is assigned one output vertex, and it is going to be processed in parallel, and they are going to actually do the 3 different stages that you need to do some GNN. So here are some results that they actually show that in terms of the impact of each block in the ghost architecture on the performances of the GNN. So here they use different approaches. So here we have different types of modeling and how you can actually implement that. And in the end, basically, they so from a simulation point of view, they look at the throughputs compared to CPUs, GPUs, TPUs, and other accelerators. And what they've seen is that according to how you implement this, you can actually have some acceleration. You can have a throughput that can be up to at least 15 times larger than any kind of CPU. Okay, so for example, here they confronted with the Tesla V100, TPU for Google, and Intel Xeon CPU. They use even some different platforms for comparisons. And I mean, you can look into the details, and they use different data sets like the Cora, Sightseer, PubMed, etc. So here is to show you that already from the point of view of simulation, if you actually implement that from the point of view of the acceleration, you can have a good, I mean, already an increase in the performances. Here, very quickly, another example. So here, the idea is that we are going to use the fact that when you have a propagation of light, basically you have intensity and phase. And this is something which is typical from complex numbers, okay? So because here, I can represent that as a complex number. I can say that my field E is basically E0 A J omega T minus KZ. Okay, and basically I can encode a complex number directly on the electric field. Okay, and I can actually use this representation to actually do operations directly in complex. Okay, and for example, in this example, they've implemented that. So they've constructed, so here you can recognize a series of Mach Zehnders to actually change the intensity and the phase of the different inputs. And what they've done is that they test it for different types of training. So here they use for 2-bit logic gates, they including the XOR, which in real you cannot do. Here in complex you can. They use a single complex layer to classify Iris data sets and other operations. So here I just show you, for example, the gate. And here you can see that by training here on the, you can see the NAND, and here you have the XOR. So what they've done is that they use 2 inputs, and according to the input, they actually try to train the function to actually do the output of the gate. So here NAND, and here for the XOR. So they actually train there for that. You can do also training for linear decision boundaries. So they use it on the cycle boundary and on the spiral boundary. And as expected, for a complex implementation, you can actually get something which is much better than the real one. And you can do it directly on photonics. So here, one of the features that I wanted to highlight is the fact that once it's trained, the bandwidth is just limited by how fast you can actually put data through. Because here you've trained your network, it's there, you have all the phases that are there, and you send data, and the state of the art for transmission is around 112 gigabit per second. So you could have something that is going to do processing at more than 100 gigabit per second without no problem. And here, from the point of view of power efficiency, basically when it's set, it does it for you. So you can see here that there's always the issue on how you're actually going to feed this data. Okay, so I can go quickly. So what is the advantage of photonics? So the goal is that, okay, we've seen that the operations are literally performed at the speed of light. So basically, it's just the time that it goes through the system. You can do multiplexing. You can do a lot of different wavelengths at the same time. And metric is what gets people interested, because you can get more computing power. So you have different implementations. For example, NVIDIA, they've done a multiplier that can do multiplication at 50 gigahertz per second. You have some implementations in a photonic accelerator that can do 1 teramach in one single chip. You have less power consumption, some claim more than 100 times less than equivalent in CMOS, faster processing, but here we can also do the data management over long distances, because since the data is propagating in optical fibers, there is no need for the data to be nearby. You can put at the other side of the room. It doesn't matter, because just a few nanoseconds of delay. So it's fine. So you don't need to have everything close together. So you can actually disaggregate the different computing elements. So while the performance numbers are impressive, these accelerators need to be viewed throughout a lens of practical systems. And this is why I'm going to try to do it. From the point of view of bandwidth, yes, 2 minutes. Okay, so I need to. So maybe the thing I want to tell you is that from the point of view of performances, so here we can go. There are a lot of advantages, so you can go through it. And problem is that in the real world case, you need to actually take into account the accelerator, the memory, the host processor, and the communication. You need to take into account all of it. And that's one of the things that was done by Light Matter, where basically they claim that they managed to increase the compute density by 72 times, to compute speed up by 288 times, and to increase the performance per power by 1.7 times. So you can see here there is a lot of different. So I'm going to go through very quickly. So here is some examples, so you can go through it, and you can see that the numbers, they look nice. But here, one of the things that is important is I want to stress here is that when we look at numbers, it is important to look at the overall system. Because here, for example, we have that the optical device uses only 10% of the overall system, meaning that the 90% of the power is consumed by what is around to make it work. So the DACs, the ADCs, the RAM, the EO, the interconnects. So in the end, you can claim, okay, I have very efficient photonic accelerator, but in the end, we account for only 10% of the whole system. Okay, so it is important to remember that, okay, when you see 100 times increase, you need to think of what is the system around. So here, okay, I can, okay, so the technological, not everything is fine. There is a problem of memory bounds, how you feed the beast, okay? So how do you send enough data for these photonic accelerators to actually compute? And here, actually, there's something that is interesting is that since there are no practical memories in photonic, because you don't have it, you need to rely on electronic memories. And you need to do the conversion from electronics to optics and back and forth. So you need to use as much as possible the data once it's in the optical domain. So in this sense, whereas for electronics, you want to have complexity of algorithms that go with n. For photonics, the higher the better. So if you go in ON2, ON3, whatever, it's better, because you can actually use this huge amount of processing capabilities to actually do it faster. In fact, some demonstrations, so here is a proof of concept, that you can actually solve the easing problem, which is in 2 to the n, much better and in a very efficient way with photonics. So, and also we can use the inherent nature of light, for example, for complex, and to implement other things. So integration with photonics is also a problem. We have precision limits here, because everything I've said up to now is limited by how precisely you can encode the data, and this is a quite huge problem. So it's difficult to get precision that is beyond 8 bits. So I'll go. What is the biggest problem for now is that there is no tool chain for photonic accelerator. So basically in CMOS, you have already all the chain. For photonics, basically you have very little. So basically, new players now, they have to develop everything from ground. So, okay, so But one of the things that's interesting is that the big players are actually real big players, because you have Google interested, Facebook, Nvidia, IBM, Lightmatter, etc. So you have a lot of people that are interested in that. So thanks to this development, so the last decade of photonics computing is there. There are still many challenges to overcome. And the question is, will it stuck, or is it something like in the 80s that's really interesting, but in the end, we don't manage to actually develop it properly, and it doesn't stuck and just dies there. Okay, basically, that's it. Thank you. Thank you.
So we have time for one very quick question. Then if you have more, you can. I think he will be around, so you
Yeah, yeah.
can stop him later. Is there any question? Yeah.
Just quick question. Is it interoperable, the conversion between the parameters, weights of a neural network to the equivalent photonic engine, actually? Yeah.
I mean, your question is it something that we can do easily, or I didn't
If
get?
it's possible, actually, yes.
Yeah, I mean, that's my point is that using those modulators, you can actually put different weights and different data parameters inside. I mean, you can encode it in the optical domain.